Kinematics is all about describing motion while ignoring the agents that cause the motion. So in other words, what we're saying is we're not really interested right now in how or why the thing is moving the way it's moving. Okay? We're just interested in describing its motion. We want to, in a way, kind of become multilingual in how we describe motion. And what I mean by that is we can use vocabulary that's very specific to describe the motion of an object in words. We can also use graphs to describe the motion of an object, and we can use equations or models of the motion. All right, all of those things are things that we're going to be covering in this chapter. But we don't have to worry about, well, why is it doing that? All right, that's for later. That's what we call dynamics. Okay, for now we're going to worry about motion in one dimension along a straight line. So I want you to imagine object moving back and forth, not moving along any sort of diagonal path or moving through the air or anything like that. We will talk about, if we do talk about moving through the air, something falling or rising straight up and down, but not moving along like a diagonal path. Okay, and we're going to use the particle model. All that means is that the size of the moving object has no impact on how we describe its motion. Okay, whether we're talking about a freight train or we're talking about a marble, we're going to describe its motion without accounting for the size of the object. All right, so that really has no bearing on what we're doing right now. Okay. All right. So the first term that we need to talk about is position. Okay, and you'll notice it says here position is defined in terms of a frame of reference. All right, here's what I want you to imagine right now. Imagine that I said to you, I want you to describe what my position in the room is right now. And I asked you to write that down. All right. Some people might say something like, oh, he's about 5 feet in front of me. Some people might say, oh, he's about 2 feet in front of the board. Or he's about 2.5 meters from 2.5 meters to the right of the door. Okay. He's about 3 meters to the left of the window. I want you to notice what all of those things have in common. The thing that they have in common is a frame of reference. You always describe an object's position relative to something else, right? So your frame of reference is your origin. It's where you're measuring off of, whether it be the board or the table or yourself or the door or the window. All right, it's your frame of reference. Okay, so when we really define what position is an object's location with respect to the frame of reference or the origin point. All right, it's an object's location with respect to that point. You'll notice that I wrote up here a couple of things in purple. So I wrote meters. The standard unit that we're going to use to measure position is in meters. Could we use feet? Sure. Could we use inches? Sure. Could we use centimeters? Sure. SI unit's going to be meters. Okay, you'll notice I wrote the letter X here. That's because when we're using equations in physics, the letter X stands for position. In your math class, you're probably used to using X for any given variable. That's not the way it's going to work in physics. If we're looking for X, we're looking for position specifically. If I'm looking for velocity, I'm not going to use X. If I'm looking for acceleration, I'm not going to use X. Okay? So position is X. And you learned about vectors and scalars. Position is a vector. And the reason it's a vector is because it has two pieces of information. It has information about an amount, and it also has information about a direction. He's 2 feet in front of the board, right? So the 2 feet part is the measurement part. That's your magnitude. The in front of is an indication of direction. So position is a vector because it has both of these pieces of information. Okay? All right, now, let's talk about distance. So distance, by definition, is the length of the path traveled by an object. So I want you to literally think about Imagine an object moves in whatever random path it moves. I want you to imagine taking a piece of string and stringing it along the path that the object took. How long is the piece of string? That is what we mean when we talk about distance. Because that's the case, it's ignorant of direction. It doesn't matter which way you go. When you look at the mileage on your car, it doesn't tell you, oh, you went this many miles north and this many miles east. It doesn't say 0 when you drive back home. It just traces out the path that you took and how much total distance did you travel, how much total length of path did you travel. Okay, so it doesn't depend on direction. It is also measured in meters. That's why sometimes people get distance mixed up with position. Same units. But the symbol for distance is going to be d in an equation. Okay. And then we're going to talk about displacement. All right, so displacement is defined as the change in position during some time interval. So an object started at some position, later on it ended up at some other position. It's obviously now at a different position than it started. How much different is it? That's what we mean by displacement. Okay. You'll notice the symbol for displacement is delta x. All right, the little triangle is your delta symbol. I want to remind you that the delta symbol, anytime we see that symbol, it means change in something. So in this case, change in x, change in position. Whenever we calculate the change in something, it's always going to be the final minus the initial. If I wanted to know how much has your height changed since the time you were 4 years old, we can measure your height now. We can see what your height was when you were 4. And we take your height now minus your height when you were 4, not the other way around. Final minus initial, not initial minus final. Okay. The units for displacement are also meters, and delta x can be positive or negative, because really what the positive and negative tell us is whether the object is, let's say, to the right of the origin or to the left of the origin at the end. It's an indication of direction. The sign on displacement tells us about direction. Okay? And it's different than distance, which is the length of the path followed by a particle. So I'll illustrate an example in a second. Any questions so far? Okay, so imagine we have, let's say, 2 points A and B on a map. All right. I could, theoretically, take a path from A to B like this. All right. Or maybe I could take a path from A to B like that. Or I could take a path from A to B like that. Or, I don't know, let's get fancy. What do we want to do? Creative? Yeah, let's try that. We could take this smiley face path from A to B. Or we could take this star path from A to B. Okay? All of those paths have different distances. They have different lengths of path. We strung a piece of string along each one. Every single one of those paths has the same displacement, because you started at A and you ended at B. The change in position from there to there is a set value. You went so many meters, let's just say for now to keep it simple, northeast of where you started. Okay? You can get more specific than that, but we're not going to do that now. So that is the difference between distance and displacement. Distance, you have to worry about the length of the overall path. Displacement, you have to worry about where did you start, where did you finish, what's the change. What happens in between is really not important. Okay, and it's going to turn out that using displacement instead of distance to make measurements is actually going to be more accurate in the long run. And we're going to see about why once we start getting into speed and velocity in our next lesson. Questions? All right, so let me talk to you about what you need to do